A warm welcome to the second lecture on the subject of digital signal processing and its applications. In the first lecture, a very brief lecture, we had essentially introduced the theme of digital signal processing. In fact, let me make a remark here, having completed the discussion in the first lecture. We had said that our objective in this course is essentially to discretize the independent variable and make do with that discretization. Looks like a very simple task. After all, you are just seemingly constructing an equivalent signal and obviously then constructing equivalent systems, whatever that might mean, and you are carrying out the same task as you would on the so called continuous signal or analog signal, as the literature would call it, on the corresponding sampled signal. The task is much more difficult than it seems at first glance, and it would take us quite some lectures to build up the whole framework in which we can do this. We intend to begin doing this from the lecture today. Now, let us first put down the objective of the lecture today and then expand upon that subsequently to look at how we are going to build up ideas in the future. So, in today's session, the objective is to answer the following question. What is a satisfactory way in which we may discretize a signal? We need to put this question down in so many words, because we need also to identify a little more rigorously what we mean by some terms that we have used. Two important terms which we need to expand upon are satisfactory and discretize. We understand these terms intuitively, but we need to bring about a slightly more formal understanding of these terms. Now, let us take the first term, satisfactory. What do we mean by satisfactory? Well, by and large, what we mean by satisfactory is not losing information, so to speak, not losing something that is critical. So, you see, we need to ask whether the process of discretization causes us to lose something, and if so, what does it cause us to lose? The second term, as I mentioned, that we need to identify and understand is the term discretize. What exactly do we mean by discretize? Of course, we have an intuitive understanding. To our understanding, discretize means use only the values of the signal chosen values of the independent variable. And very often this process has been called the process of sampling. So, for example, let us take an audio signal. In audio signal, the independent variable is time, and the simplest thing to do is to choose the values of the signal at uniformly spaced points. So, suppose we have this, I will just sketch an audio signal. Let us assume that there is a voltage waveform corresponding to the audio signal. In fact, now let us start using some notation. We shall denote the independent variable without any loss of generality by t. In fact, very frequently the independent variable would indeed be time, and therefore, we shall use t to denote the independent variable. Also, without any really serious loss of generality, we will use x of t to denote the independent variable, the dependent variable. Okay. So, x of t as a function of t. Now, again let us go back to the definition that we had just put down. Discretize means use only the values of the signal at chosen values of the independent variable. So, we have to put down a process of choice, right. What is that process of choice? The most obvious of the processes is to choose what is called uniform sampling. Uniform sampling means take values of the independent variable which are spaced with the same spacing between any two successive instants. So, for example, let us go back to the signal that we drew a minute ago. Let t be what is called the sampling period here. And let this be the point small t equal to 0. What we are saying in effect is we are going to take the values of the signal at capital T, capital 2t, capital 3t, 4t and so on this side, and at minus t, minus 2t and so on this side. So, we are going to use these values which we would call samples. And of course, we want then to satisfy that basic definition that we had when we spoke about being satisfactory. Satisfactory meant not losing something that is critical, and we need now to understand what it is that is critical, or how we can judge whether we are losing something that is critical or not. Now, let me spend a minute in putting down an approach. You see, what we are first going to do is to try and answer this question in the context of one of the most used or one of the most frequently referred to waveforms in the literature, the sinusoid. I shall say a lot about the sinusoid or the sine wave as it is popularly called at different points in this course. But at this point in time, I want to spend a couple of minutes in, if you may want to call it that, extolling the virtues of the sine wave. And the reason why we base our thinking in signal processing, or at least in a first course on signal processing, on the sine wave. So much are signal processing engineers or people who undertake research in signal processing, so much are they fond of the sine wave that they tend to think of all reasonable signals as comprised of sine waves. Now, you may wonder why this is the case. Why the sine wave? Why not a square wave? Why not a triangular wave? Why not some other peculiar kind of waveform, which might also have some interesting characteristics? Well, one of the important reasons is that the sine wave is probably one of the smoothest functions that one can encounter in nature. Smoothest in the sense that if you look at the derivative of a sine wave, it is a sine wave of the same frequency. Add two sine waves of the same frequency and you get a sine wave of the same frequency. When you integrate a sine wave, take the indefinite integral of a sine wave of a particular frequency, you get a sine wave of the same frequency. So, sine waves in that sense have a persistence in their existence under several operations: differentiation, integration, summation of sine waves of the same frequency. And what is beautiful is that when you are talking about sine waves, and if you are dealing with sine waves of a particular frequency, under these operations the frequency remains unchanged. Now, let me just to convince you about the salient nature of the sine wave in this context, take a couple of other waves to show the contrast. So, let us take the triangular wave in contrast. You can visualize this being repeated. Now, visualize another triangular wave of the same frequency, but displaced. Now, of course, same frequency, by same frequency, firstly of course I mean that this wave is periodically repeated and that the period is the same. So, you know, this period from here to here is maintained. Let us call that period T1. I draw another triangular wave, perhaps of a different amplitude, if you please, but the same frequency. It is a little displaced here, and this interval is also T. Do not worry too much if the drawing is not so accurate, it is a sense which is to be conveyed. Now, it is very, now of course, this would continue downwards here, and this would again go upwards there, and so on. You could continue and complete this. Anyway, the idea that I am trying to bring out here is that when you add these two sine waves, or rather non-sine waves, when you add these two periodic functions, what you get is of course a collection of straight lines. So, you know how to add waveforms like this. You would have to first divide it into segments which comprise of straight lines of the same kind. So, let us take this segment for example. Here you have a sum of two straight lines, which is going to be another straight line. And of course, when you have 2 points on a straight line, the straight line is determined completely. So, at this point, for example, you would have essentially this, and at this point you would have the sum of this and this. You would have to take essentially, if this height is h here, then you would have to place h above here like this and join this. So, I will do that by using a dot and a dash. Now, after that you could sum up these two segments of the straight line, and you can keep doing this. I mean, you have to keep dividing this triangular wave or pair of triangular waves into small segments, each of which are straight lines, and the straight lines do not change in that segment. So, here the straight line is changed from here. So, you cannot include this part and this part in the same segment, you have to use different segments. And the moment one of the straight lines changes, or the moment one of the small straight line segments comes to an end, you need to change the segment over which you are adding. So, anyway, you can see that here again you will have another sum of that kind. So, here it is going to be this plus this, so twice of this, whatever it is. And you can keep drawing. I mean, I will not complete this, I leave it to you as an exercise to complete the sum. But what is not too difficult to see is that when you add these two triangular waves, albeit of the same frequency, they do not give you a triangular wave of the same frequency. That is what we lose when we talk about triangular waves. Now, of course, something very similar is seen in the context of square waves. I shall just make one drawing to explain this to you. So, perhaps if you were to take two square waves of the same frequency, let me use two square waves where the positive and negative periods are equal. I will just draw a couple of periods of these, and this can continue here, this can continue there. Now, if you just displace this, so let us displace it, if you like, by half of the half period, if you like to call it that. So, you can visualize that now it is very easy to add these two square waves. Adding square waves is very easy. Of course, you can use the same idea. There are small segments here of straight lines, and you can add straight lines. When you add two straight lines, you get a straight line. That is easy to do. Now, for example, let us take numbers here for variety. Suppose this is 4 and this is minus 4, and therefore, if this is for variety half of that amplitude, 2 and minus 2, then in this region you would have 4 minus 2, so you would have just 2. So, I will just show a dot and dash here, and here you would have 4 plus 2, that is 6, and this could then continue. You can keep drawing this. So, here it would be, of course, minus 4 plus 2, so you have minus 2. Okay. So, again I leave it to you as an exercise to complete the sum. Anyway, for square waves being added, we have the same problem, and I think we should put it down in so many words. When we add two triangular waves or square waves, of the same frequency or of the same period, we do not get the same kind of wave. Of course, they look like combinations of straight line segments, that is all right, but they are definitely not square waves as we knew them in the beginning, or triangular waves as we knew them in the beginning. So, in that sense, now we understand how unique this property is for sine waves. You know, when you add two sine waves of the same frequency, you get a sine wave of the same frequency. In fact, now let me give you a justification of that. I will leave the details of the justification to you, but if I have two sine waves of the same frequency, A1 say cos omega 0 t plus phi 1 plus A2. Now, I am even giving them different amplitudes, but the same frequency. I am also giving them different phases. I can always decompose each of these, isn't it? So, I can decompose them. Let me decompose them into their cosine and sine components. So, I have this is A1 cos phi 1 plus A2 cos phi 2 times cos omega naught t minus A1 sin phi 1 plus A2 sin phi 2 times sin omega naught t. And it is a simple trigonometric exercise to combine this back again to get a term of the form A3 cos omega naught t plus phi 3. I leave it to you as an exercise to complete the details. That means, find A3 and phi 3. What are they? It is a simple exercise. I mean, it is a simple exercise in basic algebra, trigonometry, whatever you want to call it. Anyway, this proves this beautiful property of sine waves. So, now there is one good reason why we like to build our thinking around sine waves. We very often think of, as I said, all reasonable signals as a combination of sine waves. We like to think of them like that. In fact, you may wonder if sine waves are so smooth. Smooth means they have an infinite number of continuous derivatives. In fact, there is a term used in the literature for such functions. They are called analytic. They have an infinite number of continuous derivatives. If sine waves are so smooth, how is it that they come together and form rough functions? And we know that they do that to a certain extent, and they do create trouble at discontinuities, but we will not get into those details at the moment. What we do know, and we have been exposed to this idea from our introductory courses on signals or signal theory, or our introductory courses on transforms, that we can use what is called the Fourier transform to decompose or to regard a continuous signal x t as a possibly infinite sum or linear combination I will continue this as a possibly infinite sum or linear combination of sine waves of frequency varying in principle from 0 to infinity. I repeat that because it is an important idea. The Fourier transform regards a continuous signal x t as a possibly infinite sum or linear combination of sine waves of frequency ranging all the way from 0 to infinity. Now, of course, if the waveform is inherently periodic, let us for the sake of argument take the period to be 1 millisecond. Then we have associated with that waveform what is called a fundamental frequency of the reciprocal of 1 millisecond, namely 1 kilohertz. And in that case, you do not need all these frequencies from 0 to infinity, you need only discrete frequencies. You need the frequencies 0, 1 kilohertz, 2 kilohertz and all multiples of 1 kilohertz. On the other hand, we could take this argument to its limit. So, suppose you have an aperiodic waveform, a waveform where the period is notionally not finite, and that holds the key to generalization. So, if you have an aperiodic waveform and if it is quote unquote reasonable, I cannot qualify that at this time, let us assume and let us be satisfied with the explanation that we will only deal with reasonable signals most of the time. But anyway, if the signal is reasonable and if it is aperiodic, then you could think of it as if it had a period of infinity, and that means its fundamental frequency would tend towards 0. And in contrast to the case where you had a 1 kilohertz fundamental frequency and you needed only frequencies which are multiples of that, now you need multiples of what is potentially a 0 fundamental, which means you need essentially the continuous frequency axis. So, for aperiodic waveforms, we need to move from a discrete frequency axis to a continuous frequency axis. Anyway, you see, it makes it clear why we are in a position at least to deal with all reasonable signals if we can deal with one sine wave. If we can see what happens to one sine wave when we sample, we will be able to come to a conclusion on what happens to any reasonable signal when we sample. So, now let us answer the question. Let me take just one sine wave. So, let that sine wave be a cos omega naught t plus phi, or if you like a naught cos omega naught t plus phi naught. And let us sample this sine wave at t equal to all multiples of the period capital T. Let us give this signal a name. Let us call this sine wave x of t. And therefore, we are essentially taking x of n t. And we shall again use a slightly compressed notation for this. We will say x of n t is x square bracket n. Now, let us make some observations. It is very easy to see that if you had x of n t or x square bracket n, as we have just called this, which of course now would become a naught cos omega naught n capital T plus phi naught,